Hi everybody, I hope it's okay that I do this presentation in English. Yes? Thank you very much. Thank you so much. So, is the picture okay? Can you all see and read the slides? Yeah. Very well. Okay, so as you see, it's talk about container networking. My name is Dirk, I work for a company called Dynatrace. We're in the field of digital performance management and application performance management. I suppose most of you have already heard of Dynatrace, so I won't go into detail what we're actually doing. I'm part of a team that's called Innovation Lab, so it's part of my job to research new and emerging technologies, to research on them, so build prototypes, talk to prospects and possible customers, how they are going to use this technology and if they're going to use it at all. And yes, write blog posts about it, so you see also the link to my blog and to my Twitter handle, so you can check it out and follow me and follow up with any questions that you might have using this coordinate. So I want to find a little bit out of about the technology level of the crowd that's here today. It's a really big crowd, and let's say I held a similar talk once in New York, and I did a joke as an intro, and I will try it here as well. Did not go that well, but let's see how it works here. Because it is a networking joke. It's about UDP, but you might not get it. Okay? At least a few laughed. That's more than I got in New York. To all the people that didn't laugh, we're gonna get to the point, to the ground of that joke in a little time. So what I want to know, how many of you have ever done anything with Docker containers? Show of hands. A lot of people. How many have done something with container overlay networks? You little. Okay, then I think it's a good fit, the topic, to, let's say, broaden your horizon on network overlays in combination with Docker containers or containers as such. So what I'm going to talk about, I give a short introduction about containers. I think the majority of the crowd has already worked with containers, so I will keep it short. Then we're going to take a look about how we're going to give network functionality to a container, how actually container networking on one host works. Then we're going to talk a little bit about software-defined networking, because that's kind of the point when it comes to network overlays. So I give a short introduction to that. I won't lose too much time here. And then we're going to see how two containers that are even on remote hosts can talk to each other in detail. So we're going to dive down to Wireshark dumps, so we're really seeing what's going on the wire. And to sum it up, I will talk about some, let's say, pitfalls, and let's say after the theory, just put some points out there that you might come across when you start using network overlays. Okay, let's start with containers. So most of you used containers. You know that from a historic perspective, all of the technologies that are used to allow us to do containers have been around for many years. That's control groups, namespaces, and change root, for example. So there were the LXC containers, then it was Warden containers, they became Garden containers. Then in 2013, Docker came into place and sort of claimed this whole container space for itself. And they were very successful because they also provided an ecosystem where you can download pre-built containers with applications that are pre-configured and that just run out of the box. So that's, from my point of view, the one of the reasons why Docker was that successful at that. Then a year later, CoreOS started with Rocket containers, and now 2015, the Open Container Initiative started, where sort of all of the major container contributors came together and said, okay, let's build a single, let's say, a runtime environment for all of the containers that is interchangeable. So it doesn't matter if I deploy a Rocket container or I run a Docker container, it should just work the same. And this is actually what we call Run C right now. You've probably heard of that. And yes, that's what's going on in the container space currently. And all of the, let's say, Docker is compliant to Run C. There's a Garden container re-implementation based on Run C. That's Pivotal Cloud Foundry is using that right now. And I'm pretty sure that Rocket will also be at some point in time configurable to Run C just to keep up. Okay, let's see in detail how, let's say, if you start a container on your host, how the networking works. How does this container get access to the network? So, it's only blends. For me, I think you can see it fine. So this is a physical host. It has an IP address and a physical network interface. Done. Then, in order to run a Docker container, so I'm doing this on an example of Docker, you will need to run a Docker daemon. Once you start the Docker daemon, a Docker zero bridge is automatically created. It gets an IP address in a private subnet, and for the main part, it's just there until you start your first container. So you start the WordPress container. You see the command up there. You most probably know it. And what happens now when the container is started? A pair of virtual network interfaces is created. One end is put into the container. The other end is in the, let's say, in the namespace of the physical host. And those two are connected directly. So everything you send in on the one end comes out of the other end. And this network interface is also part of the Docker zero bridge. So if you set it up like that, you can ping from the host to the container, from the container to the host, and everything works fine. That's the basic setup of Docker network. So what happens if a user tries to access the outer world, so to say, just to access a web service or something? I depicted it with the use of a ping. So the container basically just reaches the physical interface at some time, and then there's an IP tables rule in place. This takes care of forwarding this traffic outside of the container. So this is that. I will switch to this side because I can see better what's on the slide. It's basically just a simple IP tables rule. You don't need to understand it in detail, but it's just a source nut to say that the traffic is forwarded outside and the response comes back and is forwarded back to the container. Now let's take the different way around. What if an outside process or person wants to access the service that the container is providing? Because usually you provide something of value in your container, a service that somebody wants to consume. So it pretty much works similar, let's say, but you have to do an additional step. You have to create the port forwarding rule. So you need an high port on your physical host. In this case, it's 8080. And you need to forward this port to one port in the container. In this case, it's 80 because it's WordPress. And in order to achieve that, you need two IP tables rules. So that's just the implementation details. So basically, IP tables is the magic glue between your container, the physical host, and the outside network. So you can access the outside network, and the outside network can access your container and the services inside. So far, so good. A short introduction to software-defined networks. So from my point of view, this list isn't complete, but at least for me, it's three things that are let's say, the groundstones why software-defined networking needed to be in place. That's on the one hand, we live in a world of permanent connectivity. Everybody is connected with his computer, with his tablet, with his mobile phone. We've come a long way from, let's say, mainframe computing to desktop computing to cloud computing to the mobile status we are in right now. And we have smartwatches and smart glasses and whatnot. And if you think about it, everything of these devices is somehow connected over a network. So without the network on the base, this wouldn't be possible. So let's say there is a rapid evolution in the devices, with the devices, and also networking sometimes seems to be the bottleneck, at least in some use cases. So there would also need to be an evolution. The virtualization of everything, we started off with virtualization of computing, of storage, of memory. You take VM, virtual machines and stuff like that, the container, a lightweight VM, some might call it the next evolution step. And to a certain extent, the only thing that is missing in the virtualization to get a holistic virtualization stack is the networking part. That's that. And there's also a paradigm shift in software development. So we went from waterfall to agile to lean to continuous integration to continuous deployment to continuous operations at some point. And somewhere along the way we started to do automated integration tests. And for that we needed to have, let's say, ephemeral test environments that only need to exist for the duration of the integration test. So if you do an excessive integration test with, let's say, you need an environment of 10 computers, and you only need it for 10 seconds because afterwards the test is done and you have your test result. It's kind of bothersome to go to a network admin and say, okay, I would need 10 computers and with this IP address and in this configuration. So it would take weeks to set that up. And basically that's why you followed, let's say, the software-defined approach. And of course, also the networking is a part of it. So you need to somehow manage to have automated network connectivity to your virtual machines or to your virtual computing instances. And with these three topics in mind, we somehow had to keep up with networking. And let's say the logical step is to just approach virtual networks and create a network virtualization. So there are, let's say, three major flavors of SDN. It's classical SDN, SD-WAN, and network overlays. I'm just going to go briefly over them. So classical SDN is the one where probably a few of you heard of OpenFlow, so to say. It's sort of a protocol that takes place in this area. So basically, up until now, you have active network components like switches and routers, and you connect to them, and you configure them, and you set the firewall rules and the port forwarding rules and stuff like that. But you do it on the device. So let's say the classic SDN approach is to do that in a centralized place, and then let a certain protocol, for example, OpenFlow or P4, which is said to be the successor of OpenFlow, push these network rules and these forwarding rules down to the active network components, and you don't need anyone to log into the network devices. So that's a brief explanation. SD-WAN is, let's say, the least software-defined of that three. Basically, it's like that. If you don't have a dedicated network line between your remote locations and you rely on, let's say, MPLS tunnels of your service provider, that are expensive. You want to have the choice. If you have traffic that is not that important, that it's okay if a packet gets lost or if the latency is higher, you can choose, let's say, your 3G or 4G internet line as well. So SD-WAN takes care of, let's say, of the efficiency and optimizing the costs of your site-to-site communication, so to say. And the third one is the network overlays, and that's actually the part that we're going to talk about for the rest of the talk, because that's the one that's important with containers. And it basically works like that. You have an underlying existing infrastructure with switches, routers, and everything, and every physical computer has an IP address, and everything just works. And then you create a virtual network on top. And we're going to see in a second how this works. This is not a new idea. You already know something like that. So encapsulation protocols and site-to-site VPNs, IPsec, SSL VPNs, and stuff like that. So it's just the principles applied that were used there to a different application. And that allows you to do the following, why you have let's say, site-to-site VPNs, where you can connect compute or physical nodes from the one side to the other side. You can now actually be more fine-grained. Actually configure that more fine-grained level, so to say. You can actually say, I want this container only to talk to this container, and you set this up in a network overlay, and everything is fine. So you have more fine-grained control about that. That's a short SDN excursus. So now we saw how the networking works with one container on the physical host. Now let's make it more interesting and talk about how two containers on two physical hosts can actually communicate with each other. So let's make the first example without software-defined networking, so without the network overlay in place. You basically start your Docker container. So I followed the WordPress example through. You have a Docker container with a MySQL database. You have a Docker container with a WordPress. And in the WordPress Docker container, you tell where the database is actually located. So it basically works like that. You have your WordPress container over here on this physical host, the MySQL server on this physical host, and you have the aforementioned port forwardings on every machine, sort of for the container to be accessible from the outside world. And what the WordPress container does, it actually connects to the public IP of the physical host and uses the port forwarding to get access to the MySQL database that runs on the host, in the container. That's without software-defined networking and overlays and everything. You just use the physical IP of the host. And that's actually not what you like to do, because if you're using orchestration tools like Kubernetes and Mesos and Marathon and stuff like that, you want that to be dynamic. You don't want to rely on physical IP addresses. So if you move that container, you would actually have to restart your WordPress, so the connection to the database is actually back again. This is not something that you actually would want. So now let's get into the topic of network overlays. You need three, let's say, prerequisites for that. On the one hand, you of course need the underlying IP framework and infrastructure that just the hosts are connected to each other and can talk to each other. Then you need a distributed key value store. Examples are etcd from CoreOS, Apache Zookeeper, and HashiCorp's console. These are actually the three that are used in let's say, greater applications. And you need some accessible ports. So in addition to the underlying IP infrastructure, if you have firewalls in place, there are some ports that need to be accessible for the distributed key value stores to work. But basically that's it. So now if we're talking about network overlays, I want to distinguish once more, there are two different types. And the one actually is an overlay, so you have an underlying network infrastructure that is depicted by the crowd. You have some sort of encapsulation protocol that is depicted by the dinghy, and you have some payload, that's the dude that's in the dinghy. And the second version is a little different, so you already again have an existing network infrastructure, and this time actually no overlays used, so no encapsulation protocols. So I was astounded myself the first time I saw it. It's pretty cool how it works, and we're going to dive into that, how that works in a second. But basically, if you take a look at the crowd there, two people stand out. So in that case, it's Danny and Linus that are watching Terry and Tess, where Klitschko just explodes the building behind them. And we're going to see in the Wireshark dump later that these two actually stand out. But they blend in, let's say, with the crowd, but there's something special about it. Let's get into the network overlay part, so the left one. So there are several protocols that are available. There is, for example, VXLAN. So you all probably know how an Ethernet frame looks like. If not, this is an Ethernet frame in bed drawn with squares. You have an Ethernet header, you have an IP header, you have a TCP header, and you have your payload. For example, some HTTP request get index HTML. Now this would be the traffic between two physical hosts, and if you think now in a network overlay scenario, it would look something like that. So try to remember the picture we saw before, where the underlying crowd that moved the dinghy across is actually the blue part. Then the dinghy itself is the VXLAN encapsulation here, and the payload, the dude that's riding the dinghy, is actually let's say the payload of the VXLAN header, where the actual payload is encapsulated. And the VXLAN header looks something like that. So it's kind of the evolution of VLANs, if you're familiar with that. VLANs actually was limited to 4094 VLAN identifiers, and VXLAN actually now has 24-bit rooms for VXLAN discrimination, so there's more space. And there's another, so there's flags and some reserved spaces for special applications and for, let's say, extension of the protocol. So all in all, it's an extra of 50 bytes that you need to transfer if you're using network overlays. And we keep that in mind because we're going to do a, let's say, performance comparison of some of these overlay networks later, and these 50 bytes will actually matter at some point in time. There are also alternatives to VXLAN. VXLAN is sort of the de facto standard. So Cisco ACI uses it, VMware NSX uses it. In the OpenStack world, if you have tenant networks, it's broadly mainly VXLAN, also the third-party network drivers for OpenStack, all VXLAN. Then there is also a Microsoft counterpart. Let's follow the GRE approach, NVGRE. The protocols NVGRE and VXLAN are basically the same, or they work at least the same, and also have the same header length and stuff like that. And then there's, for example, STD. So with VXLAN, as you saw, since it's UDP, and your network interface cards only support TCP segmentation offload. That is, if you send a package down to your network interface that is too large to put it on the wire as it is, it just hacks it up in smaller parts and then transfers it on the wire. That's not possible with UDP. So what STT did, it actually just prepended a fake TCP header to utilize this feature of the network interface card. So actually somebody did that. It sounds a bit insane, but someone did. And there's the new kid in town, let's say Geneve, and some might argue, okay, now we have VXLAN, we have NVGRE, now we have STT, why do we need another one? And the funny thing is that Geneve is actually crafted and drafted by the same people that wrote these three protocols, and they just say it's a, let's say, the best of breed approach of all the positive aspects of the first three protocols, combined together with additional extensibility. If you're interested in that, there is a link to a Packet Pushers podcast. There's actually of these three people that wrote these protocols and they discuss these protocols in depth. By the way, I will put my slides on SlideShare anyhow, so you can look it up afterwards. I will post it in the meetup. Okay, then let's take a look at actual implementations of such network overlays. So there's Docker Lib network. Probably heard of that. So after the acquisition of Socket Plane in autumn of 15, 14 actually, Docker came up with a methodology to realize such a network overlay so two containers can talk to each other. Then there's also WeaveNet, it's just a third-party implementation of a network overlay, and there's also Flannel from CoreOS, which is different flavors. One of them is VXLAN. So let's go take a look at an example how this works with Docker Lib network. You have a similar example like before. You have the WordPress container, you have the MySQL container. The one particular thing actually is that we don't have any port forwarding rules here anymore. But we still have it here, so you need to access the WordPress homepage from an external host. And now let's see how the communication between WordPress and MySQL works with Docker Lib network. And it actually works like that the Docker daemon needs an additional component. This is the distributed key value store I previously talked about. I think it's console in this case. And you need to restart your Docker daemons in a way that they are aware of this distributed key value store. And this distributed key value store is actually used for exchange of status information, of IP information, of information, which container runs on which physical host. So this is actually a really important component in that. And then you more or less create an overlay network, and I call it very creative MyNet. And if you start your MySQL container in this MyNet, you will see that it automatically gets a private IP address that actually differs from the subnet of the physical host. So these are totally unrelated right now. And if you start the WordPress host in the same the container in the same network overlay, it also gets an IP address of the same subnet, which is again completely independent of the underlying host's IP address. And basically, if you start your WordPress container, you would point it to 10.0.0.2, 33.06 to get access to the MySQL database. So there's nothing, the physical IP address of the host is not in the game anymore. So that's actually the thing you want to achieve, to have it interchangeable. So if this container is started on a different host, then you just need to update the information in the distributed key value store, and you can directly access it again. You don't mind the IP of the physical host anymore. And well, let's see how this works. I just executed a ping from the container with the WordPress host to the MySQL host. And let's take a look at the Wireshark dump, what we see. basically what we see is what we saw earlier with the badly drawn squares. So how the network packet actually is built up. You have the Ethernet address, you have the IP address of the underlying IP infrastructure. You then have the UDP header, you have the VXLAN header, so the VXLAN ID is 256. And then encapsulated within that is actually the message payload. That is the ping from the container over there to this container. And again, it's the Ethernet addresses, it's the IP header, and then it's the ICMP message that is actually the ping. So it really looks like that on the wire. And again, yes, you have the physical IP addresses, you have the let's say, network overlay IP addresses. And this is how it looks like. So just to come back to this picture, because I like it very much, the crowd is actually this underlying network. The thing is the VXLAN header, and the dude is actually the ICMP message on the bottom. It's the ping that gets transported from here to there using the crowd. That's how a network overlay basically works. So why UDP, to come back to the joke? By the way, this is me drawing, so I'm very glad that we have an awesome, talented UX team in our company. The difference between TCP and UDP, and that's the point of the joke, is that UDP is a stateless protocol. If you send a UDP packet, it's not guaranteed that it actually arrives on the destination. TCP has several ways of taking care of that and ensuring a stable transfer between two hosts. UDP doesn't do that. So now it's the valid question, why use UDP as underlying protocol? So the answer is simple. If you would have if you had TCP on top of TCP, you would have actually four TCP stacks that take care of maintaining the state of the connection. And you have a number of counters and timeouts that you would hit. And I have never tried it myself, but I'm pretty convinced that this won't work very long under a load. But if you're funny and want to try it, please let me know how it works. I actually did not do it. And what you also have, since you have two TCP stacks in place that take care of, let's say, do retransmissions and informing the other end that some packet has been dropped and it did not arrive, this would actually be redundant, right? So you would do it on the bottom layer and on the layer on top, and yes, it's just an overkill. You don't need to do that. That's why UDP is used as a transporting protocol on the underlying network. That's with the overlay networks. Now let's look at the non-overlay networks. So they are also called host-rooted networks. They are fairly new, like the overlay networks. And there are also a few examples. What did I write? Project Calico, if anyone knows that. Flannel host gateway actually works like Project Calico. It's just a different flavor of Flannel for OS. Then you also have Romana. Then Contif is from Cisco. Is their open source implementation of that. And there's also a feature that Brent Salisbury and John Willis presented at the Open Networking Summit in March in Santa Clara. It's MACLAN and IPVLAN. These drivers actually have been 5 minutes is hard. Have been in the kernels a long time, and now they are actually utilized for providing a network drive. And this is, according to their opinion, the way that the large-scale networks will go, large-scale overlay networks will go. How does Project Calico work? I have to speed up a little because there's only little time left. This is how I imagine that Project Calico actually was founded. This is not validated, so it surely wasn't like that, but I imagine like that. So this network overlays have overheads. We need to do something about that. These two dudes won't do anything, and this one do it like the internet, which actually is a good idea, but he doesn't know that. But Calico does. It just picks up this idea and applies it to network overlays. Non-network overlays, whatever you might call it. How does the internet work? You have routers of autonomous systems that are mainly maintained by your ISPs, and they talk to each other using BGP. So this router knows which IP addresses are behind it, and it tells it to this router using BGP, so everybody can access everyone in the internet. That's how the internet works. So now apply that to a data center and just do it like that. You have a host, you have a router on it, and your containers are actually let's say the IP addresses that their information needs to be forwarded to others, so others know how to can reach them, right? And it also again uses BGP. So this is how Calico works. Already said that, so it's etcd backed, no encapsulation, pure layer 3. Let's take a look at that. You know this picture? Again, a different subnet in the network overlay than on the physical host. This time the distributed key value store is etcd, and we again look at the ping, how this looks like in the Wireshark dump, and it actually looks like this. So this again is the crowd, so it's the 172.16 subnet. And there are two packets standing out, and these are these 192.168 subnet packets. And this one is actually activated, so you see the details of this packet, and you see there is no encapsulation in place. It's just Ethernet, IP, and the ICMP message. And this just works by these host routing mechanisms on each host. So again, these two guys are actually these ones. So now we will really browse through this one. You want to take care of the location of the services because, as I already talked about, there is an overhead of your protocol, so 50 bytes more, which sounds little if you just use it in smaller proportions. If you go big and you provide heavy load on that, it's actually has an impact. And you want to make sure that the services that talk much to each other are co-located, let's say on the same host, if it's containers, or at least on the same switch. And there are means, so the tools, the orchestration tools provide means for that. So it's Kubernetes pods, application groups from Marathon, fleet units and stuff like that help you with that. Connectivity problems, so if you're using Calico, there's also again a lot of IP tables in place, and your IP table contract table can actually overflow. So this is a common mistake that you have, your table is full and you can't connect anymore to any services, packets are getting dropped. If you ever encounter this, just check your syslog for a message like that, and then check how big your contract table actually is. And the notorious MTU. So if we again come back to the 50 bytes overhead, so you somehow need to, let's say, reduce the payload by that size if you're going over the internet. If you're going in a local, let's say, broadcast domain in your data center, you wouldn't need to do that. You probably have jumbo frames in place, so you have 9,000 bytes in place, so it's plenty. There's actually a whole talk about the MTU if anyone's interested. And now I will even accelerate more. With VXLAN you have 3.5% overhead. If you encapsulate it again, you already have 7% overhead, which is actually already quite an impact. And if you're doing crazy setup like that, so you run Docker on top of OpenStack, on top of Ravello, on AWS, and even AWS has a physical node at some point, then you have actually, you have 4 layers of network, let's say, virtualization on top of each other. And if we map that back to the crowd, to the people, it would actually look like that. And the message here is, you can do it if you actually really, really know what you're doing. So these dudes know what they're doing. So they're stacking people on top. They know that anyone can get hurt, but they've done it before. And this is actually a very important message here. Just because you can do that doesn't mean you should. So you actually should consider upfront what you're actually trying to achieve, and then, let's say, take the fastest and easiest and more manageable roads. So the overheads, if you stack it even more on the side. Performance comparison. I don't know how much time we still have. Few minutes, okay. So the contestants are Docker with net host. This actually means that the Docker container uses the host's network stack. It doesn't have a network stack in a namespace as it's usually, so it uses the host's one. So this is the fastest, of course. Then you have VXLAN overlays, and this is kind of representative for VNet and also for Docker Lib network. You have host gateway, so the host rooted option with Flannel host gateway, with Romana, with Project Calico. And you have AWS because it's in this performance comparison. I didn't do it. It's from Machine Zone GitHub.io. You can check it out anytime. And IP VLAN, so the newest kit on the block I just previously mentioned. This is the test setup. So there is a load generator on this side and an Nginx that serves a 350 byte response. and they are just started 250,000 requests per second and compared the latency of the different network overlay implementations. And this is actually the result. So I'm really bad with colors, but I think I know what's the outcome is. The fastest one, or let's say the one with the least latency, is the host gateway mode. Now, the net host mode, so where the native IP stack of the host is used. Then the next fastest one is the IP VLAN mode. This is what makes this so interesting for, let's say, larger applications. And the next are, I think, host gateway and AWS VPC, and the slowest one is actually VXLAN. So consider that when you're doing something like this. Why? Because performance. There are studies that if your response time increases 3 seconds, 46% of your customers will leave your page. This is a study done by Sitecore, so it's not something I made up. These are also real numbers. If your response time of your application actually increases, your revenue will go down because your people will leave and just go to faster pages. That's why, let's say, the choice of the network overlay or the way how you manage the networks in your containers is actually very, very important. And these are the 3 last points. So let's say a recommendation from my side: keep it simple, keep it manageable, and keep it fast.